In May 2019, deep underground, in giant L-shaped tunnels in America and Italy, some of the most sensitive machines humans have ever built suddenly twitch. A ripple in the fabric of space itself has just passed through Earth. It traveled for over 17 billion years to get here, and it's so faint that it stretches and squeezes everything by less than the width of a proton. Scientists get excited. This kind of ripple, a gravitational wave, usually means two black holes just smashed into each other somewhere far away. But when they look closer at this one, something feels wrong. It's too short. Half the story of the collision is just missing. For years, nobody could fully explain it. Then, in 2025, a group of physicists in China proposed something so strange it sounds like science fiction. What if this signal didn't come from a black hole collision in our universe at all? What if it leaked in from a parallel universe, through a wormhole? Let's break this whole thing down, one simple piece at a time. The signal is called GW190521. Scientists figured out it came from two enormous black holes colliding, one about 85 times heavier than our Sun, the other 66 times heavier. When they merged, they formed a single black hole 142 times the Sun's mass. Do the math and something wild pops out. 9 entire suns worth of mass simply vanished, converted directly into pure energy in the form of gravitational waves. That's the power we're dealing with. This was also huge news for another reason. Black holes normally come in two sizes we've actually observed. Small ones, under 65 solar masses, and supermassive ones, hundreds of thousands to billions of solar masses. Theory said a middle category, intermediate mass black holes, should exist too, somewhere between 100 and 100,000 solar masses. We just never had proof. GW190521 may have been our first real glimpse of one. Every black hole merger has a signature shape, almost like a piece of music with 3 movements. The in-spiral. 2 black holes spiral closer and closer, moving faster as they lose energy. If you turned this into sound, it would rise in pitch, like a bird chirping. Scientists literally call it the chirp. The merger, the actual collision. This is the loudest, most intense peak of the wave. The ring down. The newborn black hole wobbles like a struck bell before settling into a smooth sphere, still humming out faint gravitational waves as it calms down. GW190521 was missing part 1. No chirp, just merger and ring down, like someone hit play in the middle of the song. That missing piece is exactly what sent scientists looking for a wilder explanation. So, what's a wormhole really? Forget the movie tunnels with swirling lights. If a wormhole actually existed, it would look more like a strange, round window hanging in space, warping and bending the light around it. A shortcut connecting 2 far-apart points in space, or even 2 entirely different universes. Einstein's own equations, back in the 1920s, hinted that such bridges were mathematically possible. Scientists later nicknamed them wormholes. The simplest version is called an Einstein-Rosen bridge. In 1988, physicists Michael Morris and Kip Thorne, who won a Nobel Prize for gravitational wave research, came up with a fix. What if you could hold the wormhole's throat open using something called exotic matter? This isn't antimatter. Antimatter is real and behaves fairly normally. Exotic matter is a totally different hypothetical thing. Push it left, and instead of falling left like a normal object, it accelerates right. Instead of pulling things toward it like gravity normally does, it pushes them away. Now here's where things get genuinely mind-bending. In 2013, physicists Leonard Susskind and Juan Maldacena proposed something radical. What if wormholes and quantum entanglement are secretly the same phenomenon? Quick refresher on entanglement. Link 2 particles together, and measuring one instantly determines the state of the other, even if they're on opposite sides of the galaxy. It's not that they're sending each other messages faster than light. The outcome is random on both ends, so no actual information travels. It's more like a cosmic coincidence built into the fabric of reality. Susskind and Maldasena's idea, nicknamed ER equals EPR, says, what if that spooky connection is literally a tiny wormhole stitching the two particles together through spacetime? Entanglement and wormholes, two names for the same underlying thread. Why does this matter? Because it might solve one of physics' biggest headaches, the black hole information paradox. Quantum mechanics insists information can never truly be destroyed. But black holes slowly leak energy over time called Hawking radiation and eventually evaporate. So where does all the information that fell in go? If it just disappears, quantum mechanics breaks. If physicists tried to force it to escape without breaking quantum rules, they ran into an even worse problem in 2012. It implied the black hole's edge would have to be a wall of deadly radiation, the firewall paradox. ER equals EPR offers an elegant escape hatch. If the radiation leaking out is quantum entangled with what's still inside, connected by a tiny wormhole, then the information was never truly lost. It's recoverable, in principle, hidden in that radiation. There was one problem. This idea had only been proven for a perfectly neat, idealized pair of black holes. Real black holes are chaotic, constantly bombarded by debris, radiation, and randomness. So, in 2025, researchers built a model starting with a clean, symmetrical wormhole and gradually scrambled it, making it as messy and chaotic as a real black hole would be. The result? The wormhole didn't collapse. It just got longer, bumpier, and lumpier, earning the nickname the Einstein-Rosen caterpillar. But it stayed open and stable. And in most of their simulations, that dreaded firewall never showed up either. Here's the part that sounds almost impossible. In 2022, a Harvard-led team actually built a tiny wormhole, not in space, but inside a quantum computer. Using Google's Sycamore quantum processor, they created two sets of entangled particles that behaved, mathematically, exactly like a wormhole connects 2 points in space. They fed in one unit of information, watched it spread out like ink dropping into water, applied a specific quantum twist, the digital equivalent of propping the wormhole open with exotic matter, and the information reappeared cleanly on the other side. They had sent a message through a wormhole and gotten it back. Some scientists urged caution, saying the setup was too simple to be a perfect stand-in for a real astrophysical wormhole. But it proved the underlying math works, and that a quantum system can behave exactly like gravity's version of a wormhole predicts. Back to GW190521. The theory goes like this. In some parallel universe, two black holes collided normally. But instead of forming an ordinary black hole, the collision created a wormhole. One end there, one end here. We never heard the chirp because that part of the signal stayed trapped in the other universe. Only the ringdown leaked through to us, and that's why the signal felt cut in half. The researchers even explained why we only caught one short pulse instead of a fading series of echoes. Maybe the wormhole snapped shut right after, or the later echoes were simply too faint for our instruments. Is it possible? Technically, yes. Nothing rules it out completely. But even the scientists who proposed it admit something important. A normal, boring black hole merger in our own universe still fits the data better than the wormhole explanation. So, no, we probably didn't eavesdrop on a parallel universe. But this whole rabbit hole, wormhole, matters anyway. It gives astronomers an actual, testable way to check exotic ideas against real data instead of just chalkboard math. Combined with the quantum computer experiment and the Einstein-Rosen caterpillar simulations, it's building a genuinely stronger bridge between quantum mechanics and gravity, two theories that have refused to shake hands for a century. And our tools keep getting sharper. Since 2023, LIGO and Virgo have gotten 30% more sensitive, now catching a black hole merger roughly every 2 to 3 days. We've only been listening to the universe's gravitational hum for about a decade. This story is just getting started, and maybe one day, we won't just detect wormholes in the math. We'll actually find one. If you enjoyed this video, don't forget to like, share, and subscribe. Thanks for watching.